Hello everyone, and welcome back to my SV2 channel. This lecture is all about molecular orbitals. I'm going to have an introduction for you. We're going to be looking at molecular orbitals for the hydrogen molecule as well as helium molecule, and then I have a little bit on bond order calculation for you. Okay, so I'm going to start by a very interesting analogy. In Denmark, there's a place called Skagen and a beach called Grenen. It's a very special place because we have the two seas that are meeting each other, the Skagerrak and the Kattegat. Okay, now when these two seas come together, it seems that the water is somehow confused. The waves from one sea crash into the other one, and sometimes they are adding up and getting stronger, and there are other times that they cancel each other out. Okay, so we can use this idea to think about how electrons behaving. And instead of thinking electron as, tiny particles, we can think about them as waves, just like the seas, right? So these electron waves can combine, sometimes reinforcing each other, and there are some other times that they are canceling out each other. Now, if you go back to our old videos, we talked about valence bond theory, which is connecting Lewis structures, atomic orbitals, and molecular shapes. That means this theory, the valence bond theory, is explaining a lot of stuff, but not everything, right? So, for example, it doesn't fully explain how molecules get excited by absorbing the light, which is a very important concept for understanding colors, right? Okay, Okay, so that's why we're going to be looking at a little bit more advanced model, which is the molecular orbital theory, MO. And if you go back to our chapter 5, we talked about the electrons in the atoms that can be described by wave functions, right? We call them atomic orbitals. In the same way, we have molecular orbital theory that is helping us to understand the electrons in molecules using molecular orbitals. Okay. Okay, so for these molecular orbitals, they're going to be a lot like your atomic orbitals. Each MO can hold up to 2 electrons and they should have opposite spins. And each MO is going to have a specific energy level. And we can still use the, contour diagrams to present the shape and the electron densities, right, for all of these MOs, right? Now, here's the big difference. As you can understand by looking at the name, it says atomic orbitals. These are the ones that are going to be belonging to a single atom, but molecular orbitals are the ones that are belonging to the entire molecule, right? So we have atomic versus molecular orbitals, okay? Now think about two hydrogen atoms, okay? So each of them has 1 electron in our 1s orbital. And if you remember the 1s, it's the very simple spherical orbital. When they come close enough, their atomic orbitals are going to start combining, just like the waves that we have at the Greenland Beach, right? Now, the electron waves from each atom's orbital can combine in two different ways. And I'm going to explain them on the next page. Okay, so follow me on the next page. Okay, so you may have a constructive combination or a destructive combination. Starting by constructive one, the one that is forming bonding molecular orbital. So when the two waves add together, this is going to make a new orbital where we have higher electron density between the two nuclei. More electron density between the atoms means that they are pretty tightly sitting to each other and they're going to form a bond. We call this orbital as the sigma 1s, which is the bonding MO. Okay, now you may have the destructive combination, which is forming anti-bonding, and that is the case that the two waves cancel each other out. And therefore, they're going to create what they call a node, which is a region with zero electron density between the two atoms. So there's absolutely no electrons between the two atoms in your node area. Electrons in these orbital actually push the atoms apart. They try to weaken the bonding, right? So we call these orbital as the sigma 1s star, right? The sigma star is presenting the anti-bonding MO, okay? Cool. Now, when you're done with your, sigma and sigma stars, when you make all of your molecular orbitals, you're ready to start filling the orbitals with your electrons. So we know that hydrogen has 2 electrons in total. This is for hydrogen molecule, H2. According to the alpha principle, we start by, filling the lowest energy orbitals first, right? And both electrons goes into the sigma 1s, the bonding orbital, because that's the one that has lower energy. And then the sigma star, the anti-bonding, stays empty because we don't have any more electrons to put into that. Okay, so this makes the bond stable because bonding electrons, right, the number of bonding electrons is more than anti-bonding electrons. It's always good to have electrons in bonding, right? That's the one that is making the molecule more stable. The anti-bonding electrons are the ones that are weakening the bond. So you can imagine something like this. Starting by the left side, you've got the two 1s atomic orbitals, right? And they are getting closer and closer until we get the molecular orbital, the sigma 1s, right? That's the one that has less energy than the original atomic orbitals. And then we have these two that are the anti-bonding, the sigma star, right? And they have higher energy than the original atomic orbitals. So this will be the constructive combination, the good one, right? And this is the destructive combination. Okay, so take a look at the next page. Okay, so looking at here, this is the actual molecular orbitals for hydrogen molecule. Okay, so as you can see, we have 1s electron over here, and I have 1s over here, and each has 1 electron. When you form your molecular orbitals, you start by your sigma 1s, and you're going to place both of these electrons here. And then when you're looking at your sigma star, right, that doesn't have any electrons. It's an empty orbital. Okay, so all of these electrons are in the bonding molecular orbital, which is going to be sigma 1s, and it would be 2 electrons here. So that's why we write it as sigma 1s, and there's the exponent of 2 here. The 2 here is presenting the number of electrons in this molecular orbital. So this is going to be my electron configuration, right? All I have is only 2 electrons in my sigma 1s molecular orbital. Okay, now take a look at the next page. So this one is an example of, molecular orbitals diagram, and this is for helium molecule. Okay, so helium is 1s2, right? You've got 2 electrons for your helium atom, and the other one also has 2 electrons. Okay, so when you form your molecular orbitals, you're going to have 2 electrons in your sigma 1s, and then you're going to have the other 2 electrons in your sigma star 1s. So in this case, both of these molecular orbitals have electrons. You've got 2 in bonding and 2 in anti-bonding. If you look at your electron configuration, it's going to be sigma 1s, and there's the exponent of 2 because you have 2 electrons here. And then the same thing is for your sigma star, right? The anti-bonding. So this is going to be my electron configuration for helium molecule. Okay, now one of the really great things about this theory is that we can very simply calculate the bond order. You guys need to know this relationship. Your job is to count all the bonding electrons, all the electrons in your bonding orbitals, and then do the same thing for anti-bonding, right? And then take the difference of them and then divide it by 2, right? Whatever is this number, that is presenting the number of bonds that we have between the 2 atoms. So let's try that for both of these examples of hydrogen and helium molecules. Okay, so starting by hydrogen molecule. So for the hydrogen molecule, you've got 2 bonding, right? And we don't have any anti-bonding, 0. So that would be 2 minus 0, which is 2 over 2, and that would be 1. That means the bond order is just 1, so we have one single bond, right? We have only one bond between the 2 hydrogen atoms. And that is totally makes sense, right? Hydrogen is supposed to have only one bond, right? Okay, now let's do the same thing for helium molecule on the next page. So helium has 2 bonding electrons, but we also have 2 anti-bonding, right? So if you take the difference, it would be 2 minus 2, which is 0. So 0 over 2 is 0. Okay, so think about it for a moment. If I don't have any bond order, if the bond order is 0, that means the molecule does not exist, right? This is not a stabilized molecule. And we know that. We know that helium is a noble gas. It's going to be by itself. We don't expect to have any helium molecule, right? So by calculating the bond order here, we can understand that helium-2 does not exist. Okay? Cool, cool. That's about it. I hope you like it. This is actually one of my favorite theories. I hope you like this lecture. There are going to be a couple of more videos coming up on the same theory, a little bit more like advanced examples. Okay, stay tuned for that. Take care of yourself and bye-bye for now.